has an object, right? We're keeping track of objects. So when you compactify, you are adding things at infinity. Just think about the real numbers, and when you compactify, you do a circle, you add a point at infinity. But because every point here corresponds to an object that we parameterize, to add new points implies that we have to add new objects. That is the fundamental matter that inside, with the speak, we have the object that we already know, but because we're adding this extra locus or loci that will compactify the space, we have new objects to our problem. And the issue, of course, is the question here is what are we going to add? What kind of objects are you going to add? First, we have n distinct points in P2, so you have to lose something. Okay, you say, you know what, the features, they don't have to be distinct. Who cares if they are distinct or not? Just n points in P2. So in here, I will keep the points in P2, but I will lose the characteristic that they are different from each other. You can say, no, you know, I really do not care that it's P2 or not P2, but the points have to be different from each other. I cannot allow the points to collide. And if you do so, that is another choice. And this is the kind of characteristic that kind of guides the what we're gonna do. And you say, you can say, whoa, this is the wrong answer. This collection of points really is a zero-dimensional scheme. And you should think about like an scheme which have an ideal. So you always should have an ideal, always. And if you add new objects, these new objects also have to have ideas. And I think that way, like a zero-dimensional scheme. So in each choice, I'm kind of picking an aspect to prepare, and they will lead to different options for this kind of compactification of my so for the new object that I will have. And then I want to kind of next to discuss a little bit about where this choice, kind of where are the choices, where do they get us? Okay. So if you just say, I want endpoint in P2, I really don't care about anything else, then you just can take to, I should have posted, you just can take P2 to the end. You just can, here. You just can take P2 to the end, quotient by the permutation group, and that's it. This is compact, and we are done. And then what is happening is that you can have a configuration where these points kind of try to collide. This is you're in a family and they're trying to collide, and you say, I don't care, you let them to collide, and that's the space. But there are several reasons for which this solution is not satisfactory. So in the 60s, Fulton and McPherson introduced another solution. And they say, I really don't want the points to hit each other. That's not gonna happen. And I say, well, then once you have points and they're trying to get very close, so what will you do? You do a surgery in the space. You basically remove the point where they're going to collide and you attach a new variety so that you break basically the ambient space. They cannot be in the same room, essentially. You just put them apart, right? You break the space, and then now this you have points that do not collide, but you lose the fact that you are working with this P2. You have a more general variety. This compactification is called Fulton-McPherson compactification, and it has advantages over the previous one. What is the advantage? That in here, the new locus that we add is the technical word is divisorial, is not divisorial. So we have to add this kind of the complement that we're adding is not necessarily well behaved, it's not a normal crossing divisor, but in Fulton-McPherson, the construction that they did, when you do this this choice, this space is a normal closing compactification. But now, of course, the third option was, no, this is an algebraic object itself. We should always have an ideal. And in that case, the P2 doesn't break, right? But when they collide, you will have here a scheme with this non-reduced structure, and then schemes have kind of their own features and complications and so forth. And the space that you obtain here, as you have written, is called the Hilbert scheme. And here we end up with the choice that we have here is the Hilbert scheme of P2A, which is a really nice system. Sorry. So what we are running right now is that this is kind of this where I want us to get until here. And we see there, yes. Is that if we have a configuration of n on level points in P2, then you kind of have three choices when you want to compactify that. You can let the points to collide. You can break the P2. This will be your normal closing compactification. This is in some way better behaved. Or you just can keep the P2 and switch this to P2, keep it, but you will allow for non-reducers. And then each of these choices are geometrically different from each other. The parameters are different objects. And this is not just about P2, it's just you can do that for essentially any other variety. Any questions so far?
So the third one, there's no group action, there's nothing.
I mean, here right now, I'm just taking on level points. Okay. So here, I have the Hilbert scheme, right? But then now, the issue that and we can study this space, people study this space, for example, this is smooth, and so forth, is that this is not really the question that we want to ask. Why? Because you see, if I have a configuration of points and I use a change of coordinates, I obtain other kind of equations, right? But for me, this configuration of points is isomorphic to this configuration of points. For me, are kind of the same. And I should know this in here in these spaces, they will correspond to different. If you have a configuration of points, you do a projective change of coordinate, you will have another configuration of points. There will be another point. And I don't want to do that. I want to parameterize. What I want to do is I really want to consider this configuration up to a change of coordinate in P2. So up to isomorphism, wait to speak. Right now I'm working in P2, but you can also put this in another variety and then up to the automorphism of the ambient space, right? That is really the question which I want to do. I want to consider this economics class. So you can move from this problem in which you do not consider the coordinate change, the change of coordinates, the up to change of coordinates to the case with change of coordinates by a technique in algebra geometry, which is very well known at this point, which is called geometric invariant theory, or GIT. And kind of what it does is allow you to parameterize orbits within that space. It was introduced by Montfort in the 60s, developed by several people, Kempf, Professor P1, Dolgachev, and so forth. And then this technique, what it allows me is to consider, now I'm going to consider these equivalence classes of points. And I can do it either in PD or the affine space. So if you were starting this problem, you will be like, okay, Patricio, I want to understand configuration of points. What is the easiest case? The plane, right? C2, point in C2 has gotta be the easiest case. And I'm going to do that. So I already know that I have three choices. You can consider the generations are ideal, just let them collide, and then you break the surface. So for each of them, you say, well, what does it mean to be one point in C2 are isomorphic to other points in P2? You have to make that choice. You say, for me, they're isomorphic if I can auto-scaling and translation, which is kind of this group. So this configuration is equivalent to this other one if I can get there by scaling and translating.
The other way.
Oh, and then what happened is that my set of the orbit, the good ones, I just need to consider kind of these portions. And I said, okay, maybe I'm going to study these portions. The problem is that, what is the problem? And then you say that, okay, I have my problem, I'm going to study. The problem is kind of the group is not what we call non-reductive, which means that the ring of invariance. So the way that these questions are constructed is by using ring of invariance, and there is a condition that guarantees that is going to be finally generated, which is the being reductive group. And if it's non-reductive, that condition is just not kind of straightforward. I mean, there are developments, of course, for the tier one and other people, but it's just not gonna, you're not gonna be right away. So what we do, which at the moment, I was thinking about this problem when I finished my PhD. It's like, well, I'm not going to learn a new theory to be able to write a paper, so let's change the problem. So let's change the problem to P2, where the group is SL3, and then SL3 is a much better behaved group because it doesn't have characters and it's very. So, and we will come back to the C2 cases in a second, but then I said, okay, you know what? Affine points in the affine space have the problem that translation and scaling is not reductive, so I'm going to move 2 points in P2. And in P2, they are up to projective change of coordinates, which is essentially up to SL3. If I consider label points, then I can either take this quotient, in which this is the solution, which you just let the points to collide, or you can consider this quotient in which you let the P2 to break. Remember that we have different choices, right? That when we let this when we were considering this space of points not colliding, we have different choices for the compactification. So we can let it collide, or we can P2 break, and we can take discussion for that. However, when you want to do into the theory, you realize that you have to make a choice of a parameter. I'll be back in that in a second. That choice of parameter, it happens very frequently, even if you do unlabeled points. And in that case, you have the choice of the Hilbert scheme. You also have the choice of a parameter. Technically, you will pick like a generalized ample bundle in your variety, so forth. Yes.
And when you try to put these things capture on the space or space, but you still not going the same thing.
Yeah.
What is the actual case for the breaking of the
In each component.
this component?
Yeah. So what do we have? So before I talk about, I continue. Whenever we're making this portion, we have to make a choice of a parameter. And I kind of wanted to kind of introduce the intuition of why do we have to make that choice. And the intuition is that, and that happens when we do change of coordinates. So imagine that you're in P2 and you have a collection of points, right? Here next to you, and you have another point far away. And you are also change your coordinates. You have two perspectives which are the same because you can do change of coordinates. You can say all these points are going to collide, and then for you these are not moving. These are points are not moving, but these ones are colliding into a single point. And you can allow this degeneration where all points could collide, or you can say, you know, these points do not move, but the ones at infinity are just getting farther and farther away, and they are equivalent to each other.
I may say, the owl doesn't like it that you get so close to her.
Okay. And then, so thank you for telling me. So we can say this in this configuration, these points are getting very close and they don't move here, or these ones don't move, but the ones at infinity, the infinity is getting away. And because we can say that they're equivalent because we're saying up to a change of coordinates. So this means that when you take a degeneration, you kind of have to pick. Are you going to these to collide, or you are going to these points to be collinear? At infinity. Which one are you gonna pick? If you try to allow both of them, then you have problems about several limits being identified, and which I don't want to. So this is what the parameter essentially is gonna do. It's gonna help me to say I prefer add these objects, and you do not see this limit, or we have a break.
Because I can still just minimize that, we can still see it on Zoom.
Or we let these all points to be collinear. And again, if you try to do both of them at the same time, you run into the house shortness is not gonna be full because you have two limits at the same. This feature that we kind of have to pick between one limit and we have to pick between this one or this one. What it happens is that whenever you do quotient, you really do not have just usually one answer. You kind of have a family of answers, depending on if you pick one choice or another one. And then this kind of phenomenon that we're talking about is what the people call wall crossing, in which you are essentially, whenever you have a family of objects, when you have a family, either this one in which these are colliding or the ones where these points are going towards infinity, you for one from some values of the parameter, you pick this like your limit, or you pick this one as your limit, and they will give you a different. Then what it will happen is that different choices will give you different kind of compactifications or your space. So
is it clear where you cannot have both situations at the same time?
I mean, if you have those two both situations at the same time is when you have a strictly semi-stable point.
So you just prove that.
And yeah, but then the point in the boundary don't have a unique orbit because you have the open orbit and not the orbit. Okay, so all this, let me do like a pit stop here. We'll start with n points in P2. Distinct points in P2, and I was not compact, so I wanted to make it compact, and you have the choice of taking ideals, letting the just points to collide P2, I don't care, or breaking the variety. But what I really wanted is to consider up to a change of coordinates and on label. So in that case, I will do the quotient by the automorphism group, which is I just can take SL3, and then and in this case, what I will obtain are these kind of three families of of possible answers for the on-level points. And all of this share this open of the points are different. And we remember that we start with the point of my endpoints are different. So this is kind of this open is shared by the three of them. The classical example, which is in the I think that it's in every book that I have seen that teaches the technique. It's just endpoints in P2 with respect to SL3. Here, just label points. And it's an exercise on the theory to kind of classify the compactive, kind of classify the generation that can happen. And you essentially let the points to collide. And so kind of the interesting questions here are what kind of varieties will the space itself will be? That's kind of an interesting question. And it's like, for example, there is a choice of these parameters in which the whole space is just a product of two projective spaces. And something that I would love if someone, what are the other kind of varieties that can appear isomorphic to this space? This is, to my understanding, not known. It's kind of being classified for lower n. I've seen a classification for 5 and 6 points. But in general, they can be, when you change this parameter, there can be many varieties that appear as compactifications, and it's not clear which families, what kind of families can appear for.
So do you think that's possible for like arbitrary n?
No, this is true for arbitrary n. Actually,
Yeah, I mean like the whole like the whole like characterization of
no,
each.
yeah, but so what's happening is that the number of, I do expect by computational experiment that this is kind of exponential, the number of different compactifications, but it will be interesting to see, for example, is you have product of projective spaces, for example.
How can this be possible?
I'm happy to.
If you pick n to no listen, you pick n to be 5, that's 5 points in P2, right?
Yeah,
And
that's
and you blow them up. There's a unique del Pezzo surface. If in positions a unique del Pezzo surface of Steinberg group. Oh no, sorry, no. No.
So I like for example so like a question here, just let me write it, is there is no, thank you, that it was, can this happen, for example, P1 and it's not clear to me to the it is not clear to me which if can I should put an input
But a different beta.
different beta, exists a beta, exists another beta.
How this particular beta that gives this the isomorphism.
I'm happy to I will happy to talk. I can show you after that.
Okay.
Now, if you want the points to collide, then you put a beta that you can, because you are acting with the permutation, all of them has to be equal. So it kind of, it depends, and then you have the quotient where all points collide. That's not an issue. A more interesting question, which was something, in my opinion, a more interesting perspective, that was something that Schmidt, Benjamin in 2022, was to consider the Hilbert scheme, just. But in here we keep track of the generation. Now, the choice of this parameter technically is a line bundle. This is the division for the expert, where they are given in the generator for the Picard, so the value of the Hilbert scheme of P point in P. So, what is happening here? What we found is that if you take m equal infinity, which is kind of you just take a grade of the next cone, then you recover the previous case. You see non-scheme structure whatsoever. However, notice that for different m's, you can change this m, which is this parameter. For different m's, you are moving, like technically you're picking, you're moving inside the ample cone of this variety, because you're moving the parameterization. And what it does is that inside here you have collinear points, locus with collinear points, and the different schemes kind of don't like them. So you decrease that, take the locus where you have collinear points, replace them by non-reduced schemes, which they are called curvilinear, because they're completely containing a smooth curve. So you cannot do that with the you do that with the different strata of collinear points when you move in this way, and by when you reach here, you have less strata that is collinear, and more strata, and you have more and more, increasingly more non-reduced schemes. Like the limits that you see when you degenerate are non-reduced. But it happens that you can actually move beyond the ample cone. So a picture of this space is that you can say, well, you know, an idea really is an object in the derived category of people. And then really maybe the correct objects that maybe in this is no parameterizing ideas in P2, maybe what is really parameterizing is some complexes on the derived category with the appropriate stability. And if you do, you take that perspective, it will allow you to use the standard theory in having found it in the book will tell you this has to be, the division has to be ample, but you can kind of push it and then go to the no ample cone, but then you will find objects in the right category of SM. And then you have a kind of a final model. And I just kind of want to remark something. In here, the last one, you have as much as the limits you have very few collinear configurations. You allow a lot of non-reduced degeneration, non-reduced schemes, and you even allow objects which are no ideal but are kind of complexes in the right category. In the extreme, in this extreme, you have nothing about non-reducedness that's gone. You only see collinearity and the points colliding with each other. And then this compactification kind of allows you to pick. You can have prioritize collinear points, or you can prioritize non-reduced structures. At that moment, you are like, really, Patricio, I really do not want to work with non-reduced schemes. First, the classification is very difficult for higher end. It's kind of you tell me, Patricio, classify non-reduced schemes of dimension 0, length 7 or 8 or 9. I don't have it. It's not in the literature. It's just, I don't.
When you're talking about non-reduced schemes, are you referring to the fact that the points collapse? So
yeah.
the object represented is non-reduced, or is the quotient itself non-reduced?
It's the object that is non-reduced. Right, because you can, this is local, so you can take points in the affine space. So the idea is it's an ideal, has an ideal, and you just take the union. So, but you don't want to deal with that. I just one point. And then I'm willing to break the projective space. So maybe work with non-reduced. And that is kind of you can do that. And that was the only case that was known before we started looking into that was Killing Who. they show that the one-dimensional case, this is a very famous space in algebra geometry, is the model of points in P1. Let me just write there, but so what happened is that was the we work on this, is that we look at this compactification, and we show that there exists a choice or linearization in this Fulton-McPherson, such that this space itself is smooth. And the new locus that you add is normal crossing divisor. So it's a normal crossing compactification of your stuff. I should clarify something here. Maybe to clarify. So this is in here, it's a smooth and normal crossing, but what kind of thing do you see in the limit? You can remember you have P2s and you have a configuration of points. This is in the open inside. These are the objects on the open inside. And then when you take when you degenerate, so what you will find is that the P2 breaks, and you can have something like that. And this is what it will happen. It's like this union of variety. And why degenerate? So what kind of degeneration you say? You say, oh, well, I have this point. These three are trying to collide. You say, no, I'm not going to let you to collide. So you pop up a new component and you move them there, right? But now you have points here and they insist in trying to collide. You say, no, you cannot collide. And then you pop a new component and you put them there. And you can do it until you guarantee that the points are always different. But it may happen that this degeneration may have a lot of components. A feature, however, is that the combinatorial type is a tree, and the reason it's a tree is that you start with the initial space and the points are trying to collide, and you attach a new component here, and here they're trying to collide to attach a new component. But it's like you're attaching a node, and you have a tree, and you're attaching a node every time for every component. So this combinatorial type is a tree, which is kind of like relatively well behaved. These are the objects that we found. These are the objects. These are the objects we found. And when you take this perspective of Fulton-McPherson.
So is that torque?
Say again?
Is that X torque? Is that what you were trying to say? Like with all the trees and everything? We actually think of it as a torque blow up? Like how should I put it?
No, what I'm trying to say is that whenever you have a lot of variety glued together, you say, well, I mean, each variety is a vertex, and I have an edge whenever they are. That's kind of that captures the combinatorial complexity of and I'm trying to say being a tree is relatively well managed. So in here we do not have any of the possibilities we don't have anything like non-reduced schemes or things like that. It's just gonna be points, but the price that we pay again is that the variety will break in this manner. So let me this is kind of where we are. So the conclusion more or less is that when you think about points in P2, you have kind of a families of spaces related to each other. In here, you just let the points to collide and the P2 and nothing happens. And you can say, no, I'm not going to the points to collide, but I will let P2 to break, and you have a map in this direction. if you take it the on-level case, you have the you can map to the Hilbert scheme. You have a map from the Hilbert scheme as well. And then when you consider in this layer, we consider the action of a change of coordinates. So you can take the equation with respect the change of with respect to a projected change of coordinates. And as I mentioned before, in this side you have a space that keeps all the scheme structure, and in the other opposite space side you have a space that has no scheme structure but lets you break the variety. And these are kind of two different opposite directions in which you can go whenever studying the geometry of the space. And the feature like this one, for example, this one is, as I mentioned before, this one is smooth. This one the objects have are schemes. And then let me just say here, all of them, they share an option. Because they are different compactifications for the same kind of open.
So are they related by birational maps
Yes. Yeah, they're really perfect.
for any choice of polarization?
I mean, you vary the polarization here and you
Yeah.
and then the same the other way. Okay, but so this is kind of a pickle, and then but it's kind of all these spaces kind of have been done. It have been discussed over the years. So you said, well, Patricio, but you started talking about that. Also, you wanted to look at the affine space. And the problem I tell you is that the group is not reductive. There are generalizations which I need to learn it. So that's a good motivation. But then what can you do? What can I do in the meantime while I learn the generalization? So I wanted to talk about it. You can actually approach the problem with that kind of something that is from a topological perspective. You say, well, I have endpoints in the plane, but what is the plane? The plane, I can imagine that I have the projective space and I have a line at infinity. So plane of P2 with a line at infinity, potato, just sort of the same thing. So I say, you know what? I'm going to take 9 points in P2 and I will have a line at infinity that I will never touch. My points are away from this line. And then you say translation and scaling, and I say, well, I will have a subgroup of the project transformation, and I have if I impose the property that the point-wise take this line, and then I have a scaling translation. So basically, I can take the problem from C2 and transform it into a problem in P2. But I don't have SL3. The group here is a smaller group, it's a subgroup representative. Ideally, if I was trying to do the same problem that I was trying to do before, I would say, well, endpoints up to translation and scaling. I can, for example, tell the Fulton compactification portion by this group and kind of describe it, but this is not done. Because like again, you just cannot take the action by the group the way it is.
So it's still non-reductive. Just
Yeah, but this is what
your scheme is projected.
Huh?
It's still non-reductive. It's just that your scheme is projected.
Yes, this is non-reductive. Yeah, this is still non-reductive. That problem you're just not gonna get away by just renaming it.
Yeah.
And so this is not done. It can be done. I understand where the technology is by now, but it's not done. So what will you do? You say, well, this equivalence class imposed onto this scaling translation really give you an orbit, right? That's what you're talking about. You say endpoints up to translation, so you're taking an orbit, and an orbit is a subvariety in this P2 to D. it's a subvariety, and you take the closure, it's a closed subvariety. And there is something very, very interesting. So this means that for every configuration of points, I have an orbit. In another configuration, I will have another orbit. I have different orbits and these are irreducible varieties. Now, there is a space, it's not how the Chow variety that parameterizes all subvarieties of P2TM with fixed degree and dimension. Geometry class for the expert, but basically, if I'm parameterizing these subvarieties, I can all of them are parameterized by this called the Chow variety. And what this amounts is that a configuration of points until a configuration of points up to scaling translation, it will get associated this subvariety, the orbit, right? I take the closure of the orbit. And because this is compact and this is not compact, you know what I'm gonna do? I'm just going to take the closure. What this amount to take the orbit? What this amount technically to take the closure? It means that you see the orbit, but you also see the generations of the orbits. Because you think about a conic in P2. You have a conic in P2, it can break like 2 lines in P2, right? And then so whenever you have a variety, the variety can break. Or you have the 2 lines colliding. So, and the same way in here, this is an irreducible variety, and it may break into a bunch of things. I don't know what they are, but that allows me to make a closure, and I will have this compactification. And this is what the people call the Chow closure. This is called Chow closure. So, but then you lose something. Remember that we always wanted to know what objects go to infinity. So essentially, what happens is that you have your configuration of points, you make an orbit, but then, and because you are taking the closure in the space of all orbits, it will break. But there is no reason for this component to have any meaning of whatsoever, right? You don't know what will correspond. So the kind of the trick is to be able to recover a geometric generation of this, a geometric degeneration of this configuration of points based on the way in which the orbits break. And this actually can be done. Kind of a small miracle in some way. Let me just kind of jump ahead and say, for the sake of time. Remember, points in C2 and in the plane, I'm going to think I speak to and a line that I will avoid. These are the points. And in the full-time person perspective, I just have this, I break the P2 like I make union of, and this is like the generation that you will see if you think about full-time person. Now, if you take this is a configuration of point, you can take the orbit, you have a subvariety, and this subvariety may break. So you have 2 things happening. The subvariety, the orbit can break, and the Fulton McPherson technology that we were talking about allows the generation of points to break itself. But the question is how you relate here. In here, the configuration of points are degenerating, and in here, the orbit itself are degenerating. And it will be very nice if these 2 things are related to each other. And they are. What's happening? When you have a degeneration, you can recover in 2. You just say, you know, I will only consider the point that I can see inside this part. And I can consider only the point that I see in this component. You take each of the parts, and each of the parts, you can reduce it to a P2. And you only see, in here, you only see the point that you see in this part. There will be here, for this part of the generation, you get some points So you notice that you never have all the points somewhere because that's the issue. Kind of the points were spread out by the generation, but it's going to be a union of like a union of P2s with less mark points. This is in here. This is our P2s, and this is our P2s. But and the total number of points is still equal to n. But in the number of points in each of them is smaller. It's kind of less than some number and less than strictly less than n for each of them. But because you have, so what you did is that you now have kind of a union of P2 with some points on it, and your orbit break into a step and two things. And what you show is that you associate the orbit break down into subvarieties, and you're going to relate each subvariety to one of these components, and you're gonna do that by taking orbits of each one. So basically, this was your original degeneration. For each piece of the degeneration, you make a configuration of points in P2, less than the total, but still points in P2. And for each of them, for this one, you take the orbit, and it will give you something of a smaller degree. You take the orbit of this one, and it will give you a piece of a smaller degree. And when you do with all of them, you get a union of orbits. Each of them has less degree, a smaller degree. Why do they have a smaller degree? Because in here you have less than n points in each piece. And that is the fact that you have less than n points here, it means that you have a smaller degree than the generic orbit.
Degree of what?
That's the generic orbit.
Not degree.
Degree, I'm by degree, I mean the homology class. Which is if you were working with 2 So the orbit, so what's happening at the end, and I have to, what is happening, this is the picture that I wanted to communicate, is that in the Fulton-McPherson perspective, you have points in P2, and you will not let the points to collide, you will not do that, but you will allow the P2 to break into pieces. This configuration of point in P2, which is will give you an irreducible orbit generically. Now, the irreducible orbit will break. Like you think a conic, it will break in the union of lines. You know, a circle will break in a hyperplane. This can break into pieces. Well, the miracle is that each of these pieces is really an orbit itself of configuration of points that you get of each of these components. Each of these components will give you an orbit, kind of in some way of less degree, and that corresponds to each of the components of the generation. And allows you this kind of claims. What allows you to say is that that was a theorem that we did with Noah Siracusa, is that it will allow you to say that your compactification, this one that you do using Fulton-McPherson, no. This one, which was done using this Fulton-McPherson, technology. And this was this space of orbits. And there's the generations. And will allow you to, what the claim that you say that these two things are going to be isomorphic. Up to normalization, they're going to be isomorphic, and then what you do is that you relate the components of the generations with unions of orbits.
So here you're taking the Chow line bundle. Taking the Chow line bundle for the polarization?
And here you don't take a polarization. Because what you did is you took a quotient to define this space, you took a closure inside this override. I'm happy to, I'm happy to clarify that later, okay? But this one is parameterizing, all the generations with the same homology class. So you just keep all the generations all together. So, yeah, to finish, I mean, this, like I mentioned to you, the fact that this fact is not reductive means that a lot of the other portion has not been done. But I just wanted to mention that. Let me, with this I will finish. What happened is that we start with a problem in P2, problems in P2 and C. And I move everything into P2, but I have to change the group, right? Sometimes it's gonna be SL3, sometimes it's gonna be SL3. If I consider points in P2, sometimes it's going to be the translation and scaling. If I consider this is my P8, but I can consider other groups. For example, instead of fixing a hyperplane, I could have fixed a line, for example. There are other choices of groups, which is like different form to decide when 2 points are equivalent to each other. And I have that choice. I also can decide how much I let the points to collide. And that is what the Fulton person tells you. You say no point will collide whatsoever, or you let some of them to collide. And another aspect of the theory is that we can decide how much of the scheme structure we can see. This is the Hilbert scheme. We can see all the scheme structure, or we can see only some of it. And that's kind of the reason why we may have a lot of spaces and related to endpoint in P2, because there are different features, the scheme structure, the kind of equivalent relation that we're talking, and then if they can collide or not, and we can pick how much of each of these features we will see. And I think that we also said enough. Thank you a lot and stop here. One hour, right?
Questions?
Can I just ask a question about this non-reductive proof?
Yeah.
So you've got a GA and 2 GMs.
All the way around. Yeah, translation and scaling.
So the translation is what translation are you?
Yeah. So what I'm trying to say is that if you have a point in C2, which is like x comma, sorry, if you have x1 and x2, what you can do is you can, I was talking, you can scale them all simultaneously, and you can scale, and this is I misspelled, apologize.
Right.
I'm sorry, that probably is the correct group. I should have right on.
I think you want GA squared on the left and GM on the left.
Yeah, probably. Yeah, thank you.
So when you got
for the word to see.
when you've got a bunch of these points,
Uh-huh.
I mean, naively, I would think you could just sort of translate one of them to the origin, and that kills the GA, and now you've got a reductive proof.
Yeah.
So, I mean,
But
what? I mean, why is that not?
well, we did, yeah, those are 2 articles.
Okay.
Yes, we did that. So, but that technically, yes. So, but that's no. But I just you make a choice, and then what you get at the end is a toric parity.
Right.
The compactification with the toric parity. If you were working with NCM bar, it's called lossless Manin. There's a space called lossless Manin, and implies putting some weights on the points. Because you basically are saying, I have this point which is very, very heavy, and no other point can collide to it. You say, I'm going to put this point to the origin. You have one point to the origin, but you also have to put the condition that the other points don't collide there. And if you do that, you can kill, you will kill this part, and you only have a portion by this. and that would be just equalize.
Could you do something like say, well, the U invariants will be generated by like the differences that, you know, this point minus that point, something.
Probably, I have seen the paper that, you know, like, it is, yeah, if I understand the theory, how it's done, this case is particularly well behaved and it should be able to done more or less with it.
Yeah, yeah.
Because, yes, technically it should, yeah, I think that's even one, I think that, but I have not done it, that's kind of one.
Okay, yeah. That's good.
But I do expect it, I do expect to, if I can go here, I do expect to have, you expect something like that, you expect to have the full Thomas person. And then you expect to have the regular, is my understanding, and then you also wanted to relate it to the flipper scheme. Of, to figure. But none of this has been done.
Anyone? So I have one, so it is conjecture, right? So what's exactly what you are conjecturing, that those morphisms exist or that they isomorphism?
I mean, they should exist. This isomorphism,
That's your point.
that's a conjecture, but more interesting is like, this is a very well-known spaces, the Hilbert scheme of points in the plane, and they have these John diagrams, and it's very combinatorial. So one will want to do the equation and the stability condition on terms of those John diagrams, and they kind of, you should be able to say that the generations that you see correspond to these diagrams or not. That's more, like most to describe it, right? More, it's like more about to describing with compactification than anything else. And then and then this one, that will be the kind of the
Any other?